Hi, everybody. I'm Michael Garry, Shecco's editor-in-chief for Accelerate Special Issues and Online News Sites. Welcome to the Natural Refrigeration, CO₂ and FTE session. Happy you could join us here today online. We have an excellent session, a brief one, but very good speakers. Reminder that as an attendee, you can ask questions at the right of the screen under live discussion. I encourage you to do that. The presentations will be available after the conference. Let me just quickly introduce our speakers. So we have Michael May, Principal Consultant for Livingstone Consulting. He is Technology Development Executive with 30 years of business leadership in successful new product and technology commercialization in not only the HVAC and R industry, but also the energy, automotive, and aerospace industries. We also have with us Daniele Mazzola, Invention Team Lead of FTE and Technical Marketing Manager for Kysor EPTA USA. Daniele is the as I said, Technical Marketing Manager. Before being named at that position in May, he was EPTA's System Engineering Manager, responsible for all the company's R&D on systems, while supporting the local system tech offices in all markets and countries. He played a key role in the development of the FTE and ETE technologies, which we'll be talking about today. So without any further ado, I'll turn it over to Michael and he'll take it from there. Thank you.
Okay. Yeah, thank you. Let's see. Let's make sure everybody can see my screen. So first off, thank you, Michael, for the introduction. I think most of the audience would know me from my most recent role as the leader of research and development for Hill Phoenix. As you noted, though, I have over 30 years of technology and product development in several different industries. And today we're going to talk about CO₂ and one of the technologies that we feel should be adopted in the area of transcritical CO₂ refrigeration. I first want to start with thanking Kysor for allowing myself and Livingstone Consulting to join their presentation and to give an intro with regard to the imperatives behind CO₂ and why we need to move forward in this manner. I'm going to focus really on the imperative, and then I will hand it off to Daniele to give a more detailed technical review on the FTE or full transcritical efficiency technology. Livingstone Consulting, a couple of slides, was created to pioneer sustainable change for the built environment. What that really means is we want to drive and accelerate the adoption of solutions in the built environment that enable us to meet the imperatives that we face as both a society and an industry. And in particular, we basically are an outgrowth of the AB Consulting Group out of the UK, which has a track record of delivering sustainable results in the UK and Europe. And we are now looking to expand that sustainability drive into the US market with the addition of myself and Tristram Coffin, who spoke in the last session. This is kind of gets to the imperative. Climate change, you can't turn on your TV these days without understanding that climate change is now a reality for all of our customers. And so because of that, sustainable design is moving away from being, I would call it a marketing campaign or a messaging element of companies and a nice to have into an imperative. We have to basically come up with sustainable designs that will enable these solutions to deploy now and in the future. And the other application or other environmental area that is changing significantly is the regulatory environment. The US regulatory environment is definitely undergoing transformation. In particular, on the left, you see the California regulatory actions that are aimed at direct emissions drawdowns and reductions. But note that because our equipment and the services and products we provide have 20 to 30-year lifespans, we have to basically also take into account what we believe will happen in the future horizon. And with that, we have to start thinking about how are these systems going to interact with both net zero, carbon neutral, and resilient energy profiles. And, it goes without saying that an unknown future, can seem daunting. Most of our customers that we're talking to on a daily basis really don't understand the environment that is coming, and they are looking for help and guidance in figuring out what the solutions that they're going to need to deploy are. And that's what we're trying to basically propose today, us along with the technology developers that are going to present their technology solutions as we move forward, are looking to basically say that we have solutions that exist today. And this is a key point. It is daunting, it is unknown, but what we can tell you is that technology does exist that will enable a sustainable building system, including the HVAC/R applications. What we must do is accelerate the adoption and commercialization of those technology solutions. The other point we like to make is, from our understanding, it does not look like there will be a single silver bullet that will solve every HVAC and refrigeration customers' problems in the same way. We think, and the way we describe it is, there are going to be a pantheon of technologies that could be deployed and integrated to basically provide the solution that our customers need. And in particular, I wanted to point out two things. If you look at just CO₂ technology adoption, roughly it has been a 20-year journey. If you expand out from 2020, if we wait until 2040 to have the next technology adoption, we will be well behind the curve, and we will not meet the demands that both society and industry and our customers are going to put on us. So the biggest message we want to give today is that technologies exist, but the technology adoption needs to be accelerated. And that there are technologies in the market today that can provide these solutions and that are available for customer use today. And in particular, with regard to advanced CO₂, you have basically parallel compression, ejectors, and now Daniele is going to give you a deep dive on full transcritical efficiency, or the FTE solution that has been developed by Kysor. And with that, I'll hand it over to Daniele.
Thank you, Mike. Daniele, I'll turn it over to you.
Yep. Just share the screen, and hope you can see it. Good evening from Europe. I will talk about transcritical system with a focus on FTE. So the first question is, what is FTE and how does it work? The best way to explain this is starting from a standard transcritical system, standard one, like the diagram that you are looking at, and transform this system into an FTE system. So nothing new on this diagram. We have a medium temperature compressor that are discharging in a gas cooler. We have a high pressure valve that is taking care to transform the transcritical status of the refrigerant into a subcritical one. We have a flash gas tank on the bottom. We have the liquid, and the liquid we distribute to the cabinet and cold room. Meanwhile, in the upper part of the flash gas tank, there is a flash gas valve that is taking care to dispose the flash gas. That is a byproduct of the high pressure valve expansion. So standard transcritical system. So how do we transform this system into an FTE system? First of all, we add the FTE tank, and we add this tank between the medium temperature cabinet and the medium temperature compressor. The upper part of this tank is connected to the suction of the medium temperature compressor. Meanwhile, the medium temperature cabinet are connected directly to the FTE tank. The bottom part of the FTE tank is connected to the liquid line of the frozen cabinet. Another modification is that a solenoid valve, a standard common solenoid valve and on-off valve, is installed between the flash gas tank, the main flash gas tank, and the junction of the liquid line coming from the bottom of the FTE. There is a last modification. We will see later on why this last modification is so important, and is the connection of the flash gas. The flash gas is not anymore connected directly to the suction of the medium temperature compressor, but the flow of the flash gas passed through the FTE. Now, the system is FTE ready. The system now is a transcritical system with FTE. So we need to run the FTE. What we do? The most simple stuff. We just modify one parameter in the medium temperature cabinet. We decrease the set point of the superheating, meaning we are overfeeding the evaporators of the medium temperature. Why we do that? Which is the benefit to overfeed the evaporator? Well, basically, overfeeding the evaporator is a well-known technique to enhance the heat transfer coefficient. So to better exchange the cooling capacity from the evaporator to the air and ultimately to the product that is inside the cabinet. So if we are able to, thanks to the overfeeding, to increase the performance of the evaporator, we are able to rise the set point of the evaporation of the evaporator section in the medium temperature. So at the end, we save energy because the compressor will consume less because the compression starts from a higher level of pressure. So why the overfeeding of the compressor is not so common? Because there is a drawback. The problem is that we are start to collect liquid that is coming from the evaporator of the medium temperature, and we need to avoid that this liquid goes into the medium temperature compressor. And that's at the point where the FTE comes into action. We have the capacity of the FTE to collect the liquid that is coming back from the medium temperature cabinet, and the liquid is connected to the bottom. Then we reach a certain amount of liquid, and we do a simple action. We close the solenoid valve. This solenoid valve closed, and then we use the liquid that is on the bottom part of the FTE to feed the frozen cabinet. So FTE at the end is a smart way to dispose the liquid that we are collecting back due to the fact that we want to overfeed the medium temperature cabinet. When the liquid is completely disposed and we do not have any more liquid inside the FTE, we open again the solenoid valve so that the frozen cabinet can be powered by the liquid inside the main flash gas tank, like in a standard transcritical system. Once again, we start collecting liquid from the medium temperature cabinet. We reach again the right level inside the FTE tank. We close again the solenoid valve, and we start discharging the liquid to the frozen cabinet once again. So as you can see, the medium temperature cabinet are overfeeded 24/7, all year long, independently by the external temperature. And this provides to you the possibility to have an energy saving that is constant. Once you commission the system, you gain the energy saving, and the energy saving is kept for all the year. Meanwhile, the FTE is cycling up and down with this level inside the bottom part of the FTE. There is another feature of the FTE, which is quite important, and it is related to the connection of the flash gas valve. Now, usually the flash gas valve is connected directly to the suction of the medium temperature compressor. But during the warmer period of the year, when the external temperature is quite high, the amount of flash gas that is passing through this valve is quite significant. It can be half of the total mass flow. If you are facing a climate with 104 Fahrenheit, for example, exactly half of the total mass flow of the system is flash gas. So if we collect this amount of flash gas directly into the suction of the medium temperature compressor, we have a lot of drop of liquid that are damaging the compressor. And that's why the transcritical system cannot sustain, a standard transcritical system cannot sustain very high ambient temperature. But with the FTE, we are able to treat these mass flow of flash gas. And we are able to collect the drop of liquid in the bottom part of the FTE and use that liquid to feed the frozen cabinet. So another feature of the FTE is the ability to increase the reliability of transcritical system in warm environment. So let's sum up a little bit what FTE is and how does it work. You can see in the picture, we have an example of installation of FTE in US, where the FTE is integrated in the rack, and an example where the FTE is a modular, is modular and is not embedded in the rack, but is installed in the machine room as a separate and modular element. So to sum up a little bit, the good part of the FTE is that, as you can see, it is a simple design and concept. It uses very standard components that are quite common in the refrigeration world. We have a solenoid valve, we have a liquid sensor, we have a standard tank. So it's a system that is simple to explain to the technician, and it is a system that is simple to maintain and service. And this is very important because if, as Michael said before, we need to spread the use of the CO₂ transcritical system, we must have a simple system. Otherwise, if the system becomes too complex, it would be not wide used. Another good point of the FTE is that, as you can see, we are working on the evaporation sector of the system that is independent by the environmental condition. That means that FTE is a solution that can be applicable in any climate, no matter how low or how high is the external temperature. And it can also be coupled with the other technology that Michael was mentioned before, like adiabatic cooling, mechanical subcooling, or others, because all the other applications that are on the market are mainly focused on the high pressure part of the transcritical system. Just to conclude the presentation, I would like to show you some highlights of the FTE, both in US and worldwide. Just to say that last year we presented at Atmosphere that we had around the world 250 FTE system in operation. Now we reach 350, so plus 100 FTE installation in 1 year. And we have more than 1,000 transcritical systems, standard transcritical system running around the world. The smallest store, as you can see, is very tiny store. The bigger one is an hypermarket. The hottest climate that we face with FTE is in Abu Dhabi, in the Emirates. The coldest one is in Finland. And I also report here the farthest from headquarters, meaning that it is easy to explain and to run transcritical system, also if you don't have a very technical people at hand. And it's also compatible with a wide range of ratio between low temperature and medium temperature cabinets. Focusing on US, we are proud to say that since summer 2020, we have 2 stores with FTE running in US, and 3 are going to be commissioned in the fall. And as you can see, the installation has been done both in hot and humid climate and in moderate climate. We overcome the summer facing 104 Fahrenheit of ambient temperature, and the energy saving was quite good because we were able to increase the evaporation set point around 7 Fahrenheit degree. Of course, all these systems are without water support, so FTE alone was able to manage the climate condition that we face during the summer. Installation has been done in Tennessee, Alabama, Georgia, and South Carolina. Let me conclude with this slide that just to show you that this technology has been co-financed by the European Union in the effort to promote natural refrigeration and be of help to, let's say, replace the HFC refrigerant traditional system with transcritical CO₂. You can find more information on this project. EPTA and Kysor are very proud to be part of that and to help in the transition from synthetic refrigerant to natural one.
Okay. All right. Thank you very much, Daniele, and thank you, Michael, for those presentations. Very illuminating on this important technology. We've run out of time. Unfortunately, if you have any questions, I would suggest directing them to Daniele and Michael through the chat function or through email. And thank you guys for that very fine presentation on that very important technology. We'll clap.
Oh, thank you, Michael.
Yes.
Thank you.
Okay. Okay, guys.
Have a good day.
I'm gonna sign off. Thank you.